Good afternoon. Thank you for joining our session. Before we get into the subject, let me introduce myself and our test. My name is Ilsoo Byun, and I'm in charge of the departments that provide storage services for our in-house private cloud service. We offer various types of storage, and the largest portion is Ceph-based storage. We provide block, file, and object storage using Ceph. Across more than 30 clusters, we offer over 700 petabytes of physical capacity. Have you heard of Line? Yeah, Line Messenger is a popular communication app that allows users send to text messages, make calls, and share multimedia content such as photos and videos. It has over 200 million monthly active users, and it's especially popular in countries like Japan, Thailand, and Taiwan. Within the company, Ceph is used as one of the storage service for this messenger service and serves other purposes. Okay, back to the main topic. Why did we choose RocksDB as the main topic? Most users don't pay much attention to RocksDB since it serves as an internal metadata storage and regarded as a black box. However, when managing Ceph, we realized that RocksDB's performance was also an important factor to consider. As you know, a RADOS object consists of a name, data, extended attributes, and OMAP. And in this presentation, we'll focus on OMAP. What is the relationship between OMAP and RocksDB? The OMAP is stored as a record in RocksDB, allowing it to be queried through pointer lookups or iterated over using range queries. As you can see in the diagram, object OMAP is stored as a single record. Its key is a combination of object ID and the name of the OMAP. That means that all OMAP keys can be iterated using object ID. Why is it important to understand the internal implementation of OMAP? OMAP is used as a distributed key value store in RADOS gateway or Cephfs metadata server. Therefore, the performance of range queries is crucial. For instance, when retrieving a list object in a specific bucket in a RADOS gateway, it internally uses the OMAP of the bucket index object, which results in range query operations in RocksDB. How object lists managed in a bucket index? The bucket index ID serves as the prefix, followed by the object name, which becomes the key of the RocksDB record. When you request the object list of a bucket, Ceph internally performs a range query using the bucket index ID. What happens if an object is deleted? The corresponding record is marked as deleted, but it isn't actually removed physically, immediately. If you repeatedly write and delete object from a particular bucket, delete markers, also known as tombstones, accumulated over time, as shown in the diagram. As the amount of data grows and the LSM tree level deepens, it takes longer for these tombstones to be physically deleted. So a situation like the one shown in the diagram occurs. Tombstones don't disappear as quickly as you might expect by internal compaction, which is automatically triggered by RocksDB itself. Over time, the tombstone were filed up in several levels. What happens if we request a list operation in this situation, where there are too many tombstones? Yes, this shows the real situation. The list request sent by the user skips so many tombstones, consuming all CPU cycles and leaving other requests unprocessed, which results in unresponsive OSDs. What's unusual is that when this happens, the request is not delayed for a moment, but the OSD becomes fully unresponsive with 100% of the CPU core usage for quite a long time. In this case, it persisted for a whole 4 hours in the diagram. At the time, we are in quite the pickle until the cluster was recovered. So we modified RocksDB to check how many tombstones existed in its internal LSM tree. Surprisingly, we discovered a huge number of tombstones that are not cleaned up by RocksDB's internal compaction process. In the first part of the diagram, we periodically executed manual compaction, which removed the tombstones. However, starting from November 8th, we simply observed the situation, and you can see the tens of millions of tombstones accumulated in just a few weeks. After about 2 weeks, the list performance of OSD became terrible. So far, I've briefly explained how RocksDB Tombstone impacts Ceph's performance. Now let's listen from Mr. Koh about why this phenomenon occurs in more detail and how to address it.
Hello, my name is Sungjoon Koh, and I will continue the presentation. Previously, Mr. Byun talked about how tombstones create significant overhead when handling list object requests. Now let me break down how list operation work in RGW and explain the connection between RGW list operations and RocksDB tombstones in more detail. When RGW gets a list object request from a user, the bucket index service opens the bucket index and retrieves the bucket index object. This is a Redis object that holds the list of objects in the bucket. This data is split into shards with the number of shards set in the Ceph configuration. Each object's name is a combination of the bucket ID and shard number. Next, RGW goes through the sharded objects and requests to retrieve a specific number of entries, K, from each OMAP. Internally, this is handled by the RGW bucket list method, which Redis processes asynchronously. The number of entries to read from each shard is calculated using an internal algorithm. To put it simply, it's based on the total number of items requested divided by the number of bucket index shards. RGW waits until it gets responses from all the requests sent to the OSDs. Once everything is collected, the results are filtered and sorted if needed before being returned to the user. Now let me walk you through what happens inside the OSD. When RGW sends a request to Redis to fetch K entries from the bucket index, the OSD holding the target bucket index dispatches the message. Inside the OSD, there are sharded work queues. The PG ID is hashed based on the number of shards to decide which queue the request goes into. The primary log PG picks up the request from the queue and runs the necessary logic. For the bucket list operation, this involves fetching the OMAP header of the bucket index object and its keys. These tasks are also carried out within the OSD. The specific requests, OMAP get header and OMAP get keys, are sent to RocksDB as actual get keys request. During this process, RocksDB performs iterations to retrieve the data. Now, let me move on and explain how iteration works internally in RocksDB. When writing key value pairs in RocksDB, they are first written to a structure called the mem table, which resides in memory. As the mem table fills up with key value pairs, it eventually becomes immutable. Once the number of immutable mem tables exceeds a certain threshold, they are flushed to disk, and we call these files as SSD files. In this structure, when iteration occurs in RocksDB, child iterators are created for each component. For example, the mem table creates a mem table iterator, while each SSD file generates its own SSD file iterator. This iterator then look for the first key that meets the specified conditions. Based on these keys, a min heap is constructed. As you might expect, the key at the top of the min heap, such as key A in this example, becomes the first key returned during the iteration process. Once key A is identified as the first key and popped from the min heap, the current iterator advances by one step. The newly retrieved key is then reinserted into the min heap. Now, let me explain how the iterator advances internally. On the right, you can see the format of a block-based SST file. Keys are stored in data blocks, followed by meta blocks, which include Bloom filters and index blocks, and the footer marking at the end. When iterating through an SST file, let's say the iterator starts at key 1. To fetch the next key, the iterator checks key 2 and 3, but since they are delete markers, it skips them and moves on to key 4. Since the SST file is stored on disk, RocksDB iteration requires frequent disk I/O and involves substantial string parsing. We then analyzed which operations consume the most CPU cycles during RocksDB iteration. The graph on the left shows a real situation in our cluster where the TP OSD TP threads were consuming over 100% of the CPU cycles. At that point, we used perftop to identify which functions were consuming the majority of CPU cycles. As shown in the diagram, string processing and RocksDB iterator-related functions accounted for a significant portion of the CPU time. Next, we paused one of the problematic OSDs in our cluster and dumped the current RocksDB state to examine the number of tombstones. The graph on the left shows the result. The x-axis represents each mem table or SST file, while the y-axis shows the number of keys. In this graph, the red bars indicate deleted keys, we call tombstones, while the blue bars represent valid keys. From this, we observe that more than 50% of the keys in SST files in level 0 and level 5 were tombstones. On the right is a simplified diagram based on the graph on the left, further illustrating the precedence of tombstone in L0 and L5. Now let's discuss the impact of tombstones on RocksDB iteration. In this test, we analyzed RocksDB iteration on an exported database containing a single RocksDB instance. The goal was to compare the execution time for retrieving the next key under two conditions, with compaction and without compaction. As you can see in the graph, there's a significant difference in latency between the two scenarios. The blue bars represents the compacted state, typically in the range of microseconds. On the other hand, the red bars, representing the non-compacted state, show significantly higher latency, often in the range of milliseconds. In the non-compaction case, the latency spikes dramatically, especially at interval 3, where it increased by up to 8,500 times compared to the compacted case. On average, the latency was 6,000 times higher for the non-compacted case. To address the tombstone issue, we performed manual compaction on the OSDs.
Do you have any idea why it's 1,000 times more? I mean, you're saying tombstones are half of the system. Why they consume so much time?
Oh, yeah. Because when iterating the RocksDB, it needs to read the SST file and skip the deleted markers, since it is still left in the SST file. So, for example, is it enough for the answer?
No, sorry. So let's say you have half of the system is tombstone. I would expect, I know it's not the case, but that it would be twice as slow. Because why it's so expensive for us to skip over tombstone?
Maybe when we see CPU utilization, I think string parsing requires much more than compacted state, and also it needs to read much more things from the SST file.
But you're saying it's twice as much.
It could be more about the distribution of the deleted keys. If you get into a situation of chained keys that are
it's doing something which is exponential because you see a tombstone and you try to figure what you have there.
That's how I try to explain it myself for now until I listen to the end.
Yeah. Thank you. I'll continue the presentation. To address the Tombstone issue, we performed manual compaction on the OSDs. This graph represents the number of HTTP errors 499 and 503 errors over time. At the same time, we observed CPU usage, which, as previously mentioned, exceeded 100% on certain OSD. Additionally, we checked Ceph cluster status. We found that slow operations were occurring on OSD with high CPU usage. The issue persisted until approximately 12:58 when we performed the compaction. After the compaction, we observed a significant reduction in HTTP errors and CPU usage. Also, the slow ops is resolved. However, while manual compaction resolved the problem, it does not prevent errors from occurring again in the future. To address this, we sought a way to prevent slow ops caused by tombstones. After evaluating several methods, we found that analyzing the skip count could help predict OSDs likely to encounter issues. The skip count indicates the number of tombstones and duplicate keys encountered during the iteration process. For example, as shown in the diagram below, if RocksDB contains several keys and the request is made to retrieve 4 keys, the number of skips during this process corresponds to the number of tombstones encountered. While RocksDB employs optimizations like range lit, which means that skip count and tombstones won't always match exactly, this metric is still a helpful way to measure how much longer iteration take. Fortunately, this metric is already available within Ceph. By setting RocksDB collect extend stats to true in the OSD daemon and using the dump object store kvstats command, we can retrieve the skip count. We built a system to proactively compact OSDs likely to encounter issues by leveraging the skip count. The structure of this system is as follows. First, skip counts were collected from each OSD using the previously described method. These counts were then pushed as metrics to Prometheus via VM agent. Next, a cron job was configured to periodically query Prometheus for OSDs, where the skip count had increased by more than 100,000 times over the past 10 minutes. The identified OSDs were then added to the work queue of our team's automation tool for compaction. To prevent performance degradation, our system limits the number of simultaneous compaction processes to 3. This restriction is necessary because compaction can reduce write performance or, in the worst case scenario, block whole writes. Additionally, the metric collected in Prometheus is visualized in Grafana. As shown in the diagram below, we can monitor which OSDs have exceeded the skip count threshold. Next, I'd like to share an example of how our automatic compaction triggers work in practice. At around 2:46 a.m., the skip count began to increase significantly and CPU usage reached 100%. Shortly after 2:48 a.m., the compaction was automatically triggered. As a result, CPU usage decreased as shown in the diagram below. Thanks to automatic compaction, we were able to prevent errors from occurring in the cluster. The following graph shows the trend of compaction triggered over a week. The data is grouped into 10-minute intervals. At peak times, we observed that compaction being triggered simultaneously on up to 45 OSDs. In our cluster, the number of bucket index shards is set to 131, which means that RGW sends requests to all the bucket indexes simultaneously. We believe that this behavior is the root cause of the result. During our analysis of tombstones, we discovered an interesting characteristic that I'd like to share with you. The OMAP keys for bucket indexes are stored in the following format. The first 16 bytes are determined by the unique ID of the bucket index object, called onode.nid. Going forward, I will refer to it as the prefix. A period is appended after the 16 bytes. Following this, the actual OMAP key is added. For bucket indexes, the OMAP key corresponds to the object name. To analyze tombstones, we modified the SST dump tool provided by RocksDB to dump SST file storing the OMAP M column family. The output is displayed as follows. By default, the tool outputs keys and values in both hex and ASCII formats. We modified the code to print the keys type, indicating whether it is a deleted key or a valid key. For example, delete markers are displayed as type 0, as shown below. In the SST file we dumped, there were 321 different prefixes, and among them, 236 prefixes contain delete markers. This graph shows the ratio of delete markers for each prefix, displaying only those with a proportion of 5% or higher. What we can see from this graph is that just 3 prefixes account for over 80% of all delete markers. This indicates that a significant number of delete markers are concentrated in a small subset of bucket indexes. We analyzed the ratio of tombstones by prefix in other SST files as well. In this case, there were a total of 374 prefixes and 223 contained delete markers. Similarly, 5 prefixes accounted for more than 55% of the total tombstones. This pattern was consistent across other SST files, where a small number of prefixes contained the majority of the delete markers. So, what generates delete markers in the bucket index? First, delete markers are generated during user object deletion requests or as part of bucket's lifecycle management. When an object is deleted, RGW sends a request to the OSD holding the bucket index to remove the key corresponding to that object from the OMAP. As a result, a delete marker is left in RocksDB. In our cluster, we observed that millions of objects are deleted daily through lifecycle operations. Delete markers can also be left behind even when objects are not deleted. This can occur during multi-part uploads. When a client tries to upload multi-part object, it first sends a create multi-part upload request, followed by uploading end parts. At this stage, RGW also requests OSD to add the key into the bucket index OMAP. These keys are written with the format onode.nid plus object name plus upload ID and part number. When the client sends a complete multi-part upload request, all the keys written during the part upload are deleted. During our analysis, we observed cases where a large number of tombstones accumulated under a single prefix as a result of multi-part uploads. Based on the observation that tombstones are concentrated under specific prefixes, we propose prefix-based range compaction. Each bucket inherently has a different workload. For example, some buckets may only write objects without ever deleting them, while others may upload lots of multi-part objects. Additionally, certain buckets may frequently write and delete objects. Buckets that rarely delete objects generally do not require compaction. However, unnecessary compaction can cause several issues. For example, it can accelerate disk wear out, degrade write performance, and waste CPU usage, memory, and disk I/O bandwidth. To address this challenge, we propose optimizing compaction by performing it at the bucket index level. To achieve this, we plan to add a table property collector similar to the existing Compaction deletion collector. When RocksDB flushes an immutable mem table to disk, it converts the mem table into an SST file. During this process, all keys in the mem table, which are stored in the skip list, are read and written into the block-based SST file format. The table property collector calculates properties of the SST file during this conversion process. The existing Compaction deletion collector counts the number of delete markers. We plan to extend this approach by using a regular expression to count the delete markers by prefix instead. Since allocating linear space for this process could be risky, we propose using the count-min-sketch algorithm to estimate the number of tombstones efficiently. And this is the end of our presentation, and I will wrap it up. We need to understand RocksDB to ensure stable RGW operation, and when we neglect RocksDB, especially during list operations, it can lead to severe cluster outages. So these are the key takeaways. First, list objects results in significant RocksDB iteration, and second, tombstones are generated not only from object deletions, but also from multi-part uploads. Next, by leveraging skip count, we can proactively trigger compaction to prevent tombstone-related issues. Lastly, a small number of buckets contain the majority of tombstones. So we propose to perform compaction at the bucket index level instead of the OSD level. This is the end of our presentation, and thank you for taking your time to listen to our presentation.
Greatly inflating the impact of tombstones in this system. But I've been interested in the proposal you made. I apologize if I don't know already. Is it possible to constrain the amount of work that the compaction does by choosing it by prefix? Is that part of the implication here? That you can do less work than a full compaction by based on the information about prefix regions that have a concentration of tombstones?
Is your question is how can we compact?
I guess I've used a lot of words, but more basically, what changes in the overall work we're performing if we move, as you put it, if we change compaction to be on the bucket index level?
Yeah.
Because are we able to do less work per compaction by doing smaller compaction cycles or something like that by doing that?
Is your question that ranged prefix-based compaction compact less as?
Yes, essentially, more completely, what does it mean to do prefix-based compaction?
Okay. Prefix-based compaction only compact the range, only specific range of the terms, specific range of the keys. So currently, when we compact OSD, it compacts the whole SST files. But when we
so also if the RGW knew, for example, during a lifecycle run or other things, if it knew facts about the ranges that have been compacted, it could send those and request that they be compacted. In other words, if it had identified what it is, it could have compacted just those.
Do you mean when to trigger that prefix-based compaction?
You seem to be, we could do it in any way.
Yeah.
Makes sense. So the RGW knows that when it's done a bunch of deletion work, so it could do it, or you can keep track of it while it's happening.
Oh yeah. Actually, we have to decide it, but we don't have. Actually, we just have planned to collect the range, collect the tombstones by prefix, and when to trigger or how to trigger. I think we can discuss because since it is the open source community. So I want to discuss with you guys and develop it more precisely.
Two questions. First, is it even possible to ask RocksDB to do compaction with prefix? I thought that compaction is complete operation because you must scan the full SSD sets. Can you, and even if you say, I want you to do just the prefix, it's still going to go over the whole SSD unless you stop once the prefix changes.
Is it your question that prefix-based compaction reads small portion of the RocksDB?
Sorry, I'm asking if it's a function, if it's an existing API for RocksDB. Can you ask RocksDB to do prefix-based compaction?
Yes, right. We can compact by range, some range. We can specify some range to compact.
So
Not
it's something that RocksDB provides. It's an API that RocksDB provides.
Yes, RocksDB already provide. Yeah. Oh.
Have you seen the same issue when you do a ranged delete request versus a single delete request? Because I suppose in the UMAP API you have this ability to do a deletion as a range. So does the Tombstone issue still come when you do a ranged delete request?
Sorry, could you please tell me?
If you do a range delete request on a set of keys, do you still face issues with Tombstones?
When we compact full range compact, do we suffer?
No, when you do a range delete request instead of a single key delete, do you see issues?
You just have multiple. I think you do. I tried it once and it seems to be even worse. I don't know why. I didn't dig for that. I was hoping that we could do it. If we do range delete, that would come to eliminate the problem. But we didn't. I don't know why.
Oh, is it okay? Or okay. Yes, please ask me.
We have traditionally seen the same issue in our systems, but we don't know whether it was RGW issue. What we used to do is restart the slow of OSD and it used to go away. So does restarting of OSD actually performs compaction?
Yeah, when OSD starts, it first compacts the RocksDB, so I think that resolves the problem.
That's an option, right? There's a configuration option, compact and stop, which could be disabled in the middle. So that
Doesn't OSD itself have a schedule on doing performing this compaction instead of just on restart?
Actually, not. OSD, as far as I know, OSD doesn't trigger compaction, and or only RocksDB itself compact.
there's an option. There is
Yeah.
commit by Mark Nelson, PR47221, which uses RocksDB option. If you've seen too many deletions, then auto-trigger compaction.
Okay. Oh, yeah.
So it's not as efficient as yours because what you do, you synchronize and you schedule one by one, while this thing could just trigger and the whole system will do compaction.
Oh, yeah.
So you orchestrate this thing, which I think is much better. But that thing is just two line changes.
Okay.
Have you seen this pattern of accumulating tombstones and performance impact also on Ceph-based systems of clusters you have? Is it like a problem only for the RGW workload, or can you have similar performance penalties in Ceph-based deployment? I mean, Ceph-based also makes heavily use of RocksDB and OMAP. So I'm just wondering if it might suffer from similar issues.
In our experience, there are no such situations in MDS. I think it's because of the patterns of distribution of keys. So yeah, MDS doesn't show this situation.
In case of
Yes, right, index pool. Yeah.
We don't see this situation in data pool, just only in index pool.
Yes, only index pool.
It actually exists if you do mirroring, so snap, you generate and you delete them so that things accumulate Tombstone. And even if you just do any normal I/O in RBD, every time you do a write, you do a pglog entry, actually also in RGW. Every write is a pglog entry, and then you delete it. So the pglog entries is big part of Tombstones.
Oh, thank you.
That's really the case. I thought there was an optimization to eliminate that.
Have you tried changing the file size, the write-ahead log size, and did you see any impact with that?
Log size?
The write-ahead log size.
RocksDB wall.
RocksDB. We didn't configure it at all right now, at this point.
Do you have any experience trying to use the TTL option for time-based compaction?
No, I know that option, but we didn't apply it yet. Yeah.
That's basically how we solve this issue.
Thank you for sharing it.
So we experienced that delete markers occupies small size bytes. So I think it can be compacted. It cannot be compacted because of the size is small. I think the compaction algorithm considers the record size, but the delete markers has no data, so the record size is very small. So the SSD table, the range of the delete markers, isn't compacted automatically by RocksDB.
I think we're out of time, so please ask me freely. Thank you.